Hello guys, today we are going to do the quick revision of inorganic chemistry. People who are struggling with inorganic chemistry, I'm good at organic, I'm good at physical, but inorganic is my only problem, then this video is for you. So we are going to quickly revise these 4 chapters. Please let me know if you want extra chapters. Do check out our playlist, JEE playlist, NEET playlist, where you can find all those other chapters as well. Okay, so let's start with coordination chemistry. So just took this order because that would be very helpful for you to prepare for your examination. Okay, so coordination chemistry, the first type of question what you can expect is that which of the following is coordination compound? Coordination compound and double salts. So I'm going to give you a trick. Whichever having a sphere, coordination sphere, that is coordination compound. And you can able to see coordination compounds are linked with coordination bonds, and double salts, for example, alum salt or more salt, which you can, by seeing only, you can tell whether that is coordination compound or not. For example, I'm giving you the double salt, which is called potash alum. Okay, so you can see these are ionic bonds, isn't it? This is an example of double salt. Double salt means which can be dissociated into ions when we are dissolving it in water. But in case of coordination complex, you will see ions, but inside whatever there in the coordination sphere, that will not get dissociated very easily. Okay, so that is the difference. The question can be asked in this way. The next type of question is that how many ligands are there, or what is the oxidation state of central metal atom? Okay, so for knowing about the central metal atom oxidation state, you need to know the charge of the ligand. So I'm going to give few charges of ligands. So that will be useful to you to calculate the oxidation number. Say for example, if I'm having the monodentate ligand. These are type of ligands, okay? Monodentate, bidentate, tridentate, which means that many electrons it can, that many bonds it can form with the central metal atom. Okay, so for example, let's say I'm taking F minus, Cl minus, Br minus, or NH3, Cn minus. These are some monodentate ligands. Only one bond it can form at a time. OH minus, CO, or H2O also. These are some monodentate ligands. Example for bidentate ligand is that bidentate ligand means two bonds it can form, isn't it? So for example, oxalate, ethylene diamine, phenanthrene, or glycinate, dipyridine, or carbonate, important, carbonate, CO3, 2 minus, carbonate. These are some bidentate ligands, 2 electron donors. Tridentate, very few examples are there, which is ethylene, diethylene, triamine, DIEN, which is represented by DIEN, and terpyridine. Okay, and for tetra, triethylene tetramine. The most important ligand you can say that is comes under 6 hexadentate ligand, that is EDTA, ethylene diamine tetraacetic acid or tetraacetate. Okay, so these type of questions can be asked. And then ambidentate ligand. Ambidentate ligand, which means there are 2 connection points in the ligand, but it can connect through one at a time. For example, I'm taking nitrate, NO2 minus. So nitrogen can also donate, oxygen can also donate, but one donates at a time, which means that if oxygen is donating to the central metal atom, the donation will be like this. If nitrogen is donating, then it will be written as NO2. So how we can differentiate it by name is, we'll mention nitrate N. This is nitrate O. Okay, through that you will know. What else this kind of ambidentate ligand, that is cyanide. C can also donate, N can also donate. C is donating, then it is cyanide. N is donating, then it is isocyanide. Okay. Similarly, SCN. Yes, N, both. So one is this is thiocyanide, and NCS, then that would be isothiocyanide. Okay. So these are some important ambidentate ligands. Then important concept is that back bonding. So the question can be asked, the nature of back bonding and what is the effect of back bonding. So back bonding is nothing but, it's more of a written gift. Let's say carbonyl ligand is there. Okay. So which will be donating the electrons to metal, isn't it? So metal orbital which is accepting the carbonyl donation. Okay, this is our normal coordinate bond. But the electrons in the metal orbital will donate to the empty orbital of carbonyl. Okay, so this is our back bonding. So what is the use of this back bonding is that this makes the bond stronger. Okay, usually that's why the carbonyl complexes are very strong when we are comparing to other. Not only carbonyl, there are some other ligands as well, but mainly here we are talking about carbonyl ligands, which is having an empty orbital to accept the metal's electron. Okay, so then the next concept, which is oxidation number finding. So oxidation number, how you can find, I'm giving you few examples of different kind. First one, FeCN6. Whenever outside the coordination sphere we are having any metal or any element, just take it as, check whether that is a cation or anion. So here potassium, of course that is a cation. So remaining ligand coordination compound that becomes anion. Right? Okay. Let's say I'm finding the oxidation number of iron, keeping it that as X, plus Cn is a monodentate ligand, right? So 6 into -1 equal to overall charges 4 minus. So it becomes -4 plus 6, so plus 2. So this is the simplest method to find this type of ligand. What if I'm having a 2 bidentate ligand? What is this ligand? If anyone know, put it in the comment. What is this ligand? I told you already. So once again, X plus 3, this is a bidentate ligand, -3, X becomes -3 plus 6, that is plus 3. Okay. So similarly, you can find it out for other ligands as well. The exceptional case is that our carbonyl complex. Whenever you are seeing this carbonyl ligand in the complex, the ligand oxidation number, oxidation state is always 0. This is an important exception which you can expect as a question as well. Okay. Then EAN number, which is an effective atomic number. What is that number one? Which is an EAN is equal to atomic number minus oxidation state plus 2 into coordination number. What is coordination number? Number of ligands in the complex. Number of coordinated bond it have been formed. Not only ligands, number of coordination bond it has been formed. Say for example, I'm taking PONH3 6 3 plus. See, amine here, that is a neutral ligand. So whatever the charge on the complex becomes the oxidation state of a central metal. So for finding EAN, Z of cobalt 27 minus charge oxidation state, that is plus 3 plus 2 into, what is the coordination number? How many coordination bond formed? 6. So total it becomes 27 minus 3 plus 12, 24 plus 12, that is 36. Why we have to find the EAN number? If EAN number is equal to inert gas, like organ, not organ will not come, mostly it will come, or krypton, xenon. So inert gas atomic number, if that equals inert gas atomic number, the complex will be stable. Okay, so the EAN number, like we said, we got 36. So 36 correspond to krypton. So according to Zitwick, the complex will be stable. So that's why we are finding EAN number. Okay, so let's see some nomenclature of coordination complexes. Mostly the minus charged, negatively charged ligands will be named as ends with a sound O. Okay, fluorido, chlorido, bromido, iodo, like that. And the neutral ligands will not have any name, but for the positive ligands will end with IUM. Okay, so let's see the name. Let's name few complex, then we'll understand. Let me take the difficult one so that the easier one will be easier for you. Let's go with this simple one, 3Cl3. Okay, there are two ligands over here. Okay, not two ligands, one ligand. So what is this ligand? Ethylene diamine, which is a bidentate ligand. So how to name this? First of all, the cation part of the given structure must be named first. Which is cation? Our coordination complex, because chlorine outside the sphere, which is negatively charged. So 3 ethylene diamine is there. So tris ethylene diamine, right? Tris ethylene diamine. Chromium, what is the oxidation state? That is 3. Must be written in the Roman numerals. Then chloride. You said the negative ligands must be named as I or O sound. But chlorine, which is outside the ring, so we can just name it as such, just chloride. Okay. Then second example I would take, that is COCl NH3 5 times 2 plus. Once again, this is itself is an cation. So I'm taking how many? There are two ligands, right? Cl also, Cl and NH3. So in that case, which comes first? Alphabetical orderly, which will come first, chlorine or amine? Amine. So I have to write it as how many amine? Penta, 5 amine. So pentaamine, double M. Chlorido, I said no, should end with the O sound. Chlorido, cobalt 3, oxidation state, ion. Ion is given, so ion. The final example I would give you, which is more of complicated. That is CrC6H6. Why organic came into picture? Here, yes, benzene is our ligand. How to name this? I have to name with the eta. So this, two benzenes are there. How it is connected? Connected with 6 corners. So eta 6, benzene, chromium 0. 0 it's oxidation state. Okay. So this is an example for oxidation state naming, nomenclature. Let's move on to the next topic, that is isomerism. Coordination complex, this chapter is very, very, very important. That's why I'm stressing it much. So first type is ionization isomerism. These comes under structural isomerism, as you all know. Ionization isomerism. So what is that? Say for example, I'm taking, these are the simple questions which can be asked by the examiner. Easily you can score marks. Okay, so that's why I'm stressing this much, because you can expect a question like this. Okay, so the ligand in the inside and outside the coordination sphere will get changed. Okay, so that is what ionization isomer is. As you can see, here Cl2 is inside the coordination sphere, Br2 is outside the coordination sphere. But the isomer of this complex is Br2 is inside, Cl2 is outside. The ions outside the coordination sphere is getting changed. Okay, So that is one example. The next example, next isomerism, that is hydrate isomerism. Hydrate isomerism means the number of hydration. Say for example, H2O 5 times Cl, Cl2 H2O. Okay, so the isomer of this complex would be chromium H2O 6 times Cl3, and one more isomer H2O 4 times Cl2, Cl2H2O. Okay, Cl2H2O. And you can also write Cr H2O 3 Cl3 3H2. So number of hydration is getting changed. That's why these are hydrate isomerism. Then the next type would be linkage isomerism. This was asked in previous year papers as well. All those isomerism part is asked. Linkage isomerism, as I told you, the ambidentate ligands, nitro, cyano, those ligands are coming into picture here. Say for example, CO NH3 5 times ONO Cl2. The isomer of this complex is CO NH3 5 times NO2 Cl2. Okay, so the first example, oxygen is bonded. The second example, nitrogen is bonded. Okay, so linkage isomerism. The next one is coordination isomerism. So usually people will confuse between coordination and linkage isomerism. I'm telling you, without any confusion, you can answer to this question after my explanation. As we said, those for linkage is for ambidentate ligands. Okay. Then coordination means PT NH3 4 times PT Cl4. This is one complex, and the another one is that PT Cl NH3 PT Cl3 NH3. Okay, as you can see, the first example, I'm having only ammonia ligand, amine ligand, and chlorine as a ligand, as a separately. In the second one, it's combined. The number of ligands attached is same. Both are having 4 as a coordination number, but the ligands attached with this is interchanged. Okay, that's what the coordination isomerism is. Okay, and the final one, that is coordination position isomerism. Coordination position isomerism. They won't ask you much detailing, but they may ask in some other entrance examination this type of question. What happens, once again, I'm taking an example of cobalt, CO attached with NH2, O2, CO, NH3, 4, Cl2. Let's say another Cl2 is there. And then isomer of this is NH3, 3, cobalt with NH2, O2, CO, NH3, Cl, outside the coordination sphere, one more Cl. You can see the chlorine attachment is getting changed. The position of the coordination bond is changed. So that's what the coordination position isomer is. It's slightly the variant of the previous one. If you want, you can stick with the first 4 isomerism: coordination, linkage, hydrate, ionization isomerism. These 4 are very, very important in case of structural isomerism. For stereoisomerism, there are 2 types: geometrical and optical. For stereo, okay. So geometrical isomerism, I'm giving you the list. Just check in what pattern it covers and answer it accordingly, right? So let's talk about geometrical isomerism. First of all, the point to be noted is square planar complex with symmetrical bidentate will not exhibit geometrical isomerism. Square planar with symmetrical bidentate, no geometrical isomerism. What else can? So square planar, the unsymmetrical ligands of the type M, AB2, M, AB, AB. So what is the difference? AB means this is bidentate, the atoms which is attached that is different, and AB, these are monodentate ligands. A is one monodentate, B is one monodentate. Okay, so these two category can exhibit geometrical isomerism. The M, AA2, A2 type. This is very very important. This gives 3 stereoisomer. One is cis, trans, mirror image of cis. So this kind of questions can be asked, guys. Please be careful. Tetrahedral will not exhibit any geometrical isomerism. It's for only square planar and octahedral. So I'm giving you the list of geometrical isomerism pattern. Okay, coordination number 4 and coordination number 6. 6 means only octahedral. Octahedral can be of inner octahedral and outer octahedral, but isomerism part it is in general. Okay, so tetrahedral, as I said, no. In case of square planar, we have isomerism can only exhibited by M A to B2, M A to BC, M A B C D. Okay, this can exhibit 2, this can exhibit 2, and A B C D can 3. But in case of octahedral, I'm giving you the list which can only exhibit isomerism, geometrical isomerism. M A B C D E F, which is 15, M A to B C D E 9, M A to B to C D 6, M A to B to C 2 5, M A3 B C D 4. You can remember it, the numbers are getting decreased. Okay, so then M A3 B2 C 3. Then most important type, that is most asked type, that is M A3 B3 type, that is having 2. Those 2 are FAC and meridonial. This is not cis and trans, FAC and meridonial, the triangle part. Okay, you remember A4 B2 2, that is cis and trans. Then once again A4 BC also 2, that is cis and trans. So totally how many? 1 2 3 4 5 6 7 8 9. So 9 category of isomers only can show complex only can show geometrical isomerism in octahedral. 3 in square planar and these 9 in octahedral. Just remember this, compare it with the given complex, answer it. That's it. Okay, as I told you, tetrahedral will not show any isomerism, geometrical isomerism. Okay, so in case of optical, once again I'm giving you the list. So optical isomerism, it is very simple. CN4, coordination number 6, both know. So square planar, no optical isomerism. But in case of tetrahedral complex, the first type is M ABCD can show 2. The second type M AB2 that can show 2. Okay. Then in case of octahedral, the first type is M AB CD E F. The second type, which is very important type asked in many question papers, M AA to A2. The important part of this particular type is that which can exhibit cis and trans. Okay. Then third one, MAA3. And one more question can be asked. I told you that type, that is MAA2A2. The cis is optically active, trans is optically inactive. Just remember. Okay, the question will be asked from this part, this particular category. So please be careful with that. Cis is optically active and trans is not. Okay, cool. Then the next thing we have to look into, that is the theory part. Okay, so the first question can be asked from the Werner's theory. Werner's theory, what it says, what kind of question can be asked, that's more important for now, right? There can be of two type of questions. The first one is primary valency and secondary valency. I'm giving you in simple terms. Primary valency is nothing but the ions outside. It can be of chlorine. I'll give you the example, ions outside. Okay, and the secondary valency, which is ligand. Okay, let's say I'm taking an example of CONH3 thrice Cl3. Okay, if they are asking for primary valency, then your answer is 3 chlorine, so 3. If they are asking for the secondary valency, 3 ligand is present, so 3. Okay, so that is what the question you can expect from the Werner's theory. The next one is VBT, valence bond theory. So valence bond theory is so simple if you understand. The questions, there are 3 type of questions can be asked. One is from magnetic moment. Before that, let's get into VBT. VBT is nothing but you have to know the oxidation state and the ligands. That's it. Say for an example, I'm taking cobalt NH3 6 3+. Okay. So what is the oxidation state? 3+, cobalt 3+. So cobalt 3+, what is the configuration? 3D 7 4s2 is the ground state. So which will become 3D6. So 3D6 I'm drawing like this. 1, 2, 3, 4. And then 4s2, that is empty. 4s, that is empty. This is 3D. Okay. So this is 3D. How many electrons? 6 electrons. Also, I'm drawing it one by one. I'm following the rules. Okay. So now, ligand. Coming to the ligand, if the ligand is strong field, then the ions will get electrons will get paired up. If the ligands are weak field, then the electrons remains as such. So what are strong field ligand? What are weak field ligand? Here, these electrons will get paired up for ammonia. In VBT, he didn't explain what are the ligands will undergo pair up, what are the ligands will not undergo pair up. It was explained by CFT only. But after knowing CFT, VBT becomes easy. So I'm giving you the list of spectrochemical series. Carbonyl is a strong field ligand. The order increases like this. Starts from the weak, ends with the strong field ligand. So this is the order you have to remember. By doing the practice, I hope by this time you already know what are strong field, what are weak field. Okay, so mostly the questions can be asked from which ligands I can tell you. Halogens, all those are weak field. Okay, then H2O, neutral. EDTA strong, amine strong, EN strong, nitro strong, cyano strong, gopal strong. Other than this, just look into halogens. Those are weak. Okay. SCN is also weak. These are the important ligands you can expect the questions from. Okay. So now get into how to do this problem. So as I told, this is strong field. Strong field this will go pair up. So pair up means what? So the electrons will jump over there. What happened? It will get excited and then jump over here. So at the end, what would be formed? At the end, 1, 2, 3. 3 will be filled. The rest of the things will not be filled. So totally remaining 4p, 4s and 3d2. So total it becomes D2sp3 configuration. D2sp3 means what is the hybridization? So hybridization you need to know. So what is hybridization means? Once we found this, what are the ligands can be filled, no? Then you have to know the shape. Then we will come to know about the shape. So sp, mostly it will not come, but here linear, sp3 tetrahedral, dsp2 square planar, okay, d3s. Ma'am, what is d3s? That is also tetrahedral. I'll come to this in D and F block chapter. If you know, just comment it over there. sp3d trigonal vibrometer. Mostly in coordination chemistry chapter, you will encounter square planar, tetrahedral and octahedral only. Okay, so I'm giving these extra for other inorganic chapters as well. Okay, dsp3 which is square pyramidal, and sp3 d2 is octahedral, and d2sp3 is also octahedral. What is the difference, ma'am, between these two? The first one is outer octahedral, the next one is inner octahedral. Doesn't make much difference for now, so just leave it as such. Okay, so magnetic moment. So magnetic moment mu, that can be found by using this formula. Okay, n into n plus 2. Here the n is unpaired electrons. So if there is unpaired electrons, you can find the magnetic moment, which is an important question you can expect. If number of unpaired electrons, if that is unpaired, first of all, if that is unpaired, then that is paramagnetic. So only for paramagnetic substance only you can find the magnetic moment. If that is not unpaired, if it is looking like this, then that would be diamagnetic. Okay, so now I'm going to give you a trick, which is, I already told you in our previous videos, the number of unpaired electrons. This is trick. The number of unpaired electrons, let's say that is 1. Okay, the mu value will be around 1. Say for example, if you're substituting also, you'll get the same value. So 1, then the mu value will become 1.73. If the number of unpaired electrons is 2, then the mu value is 1.83. Sometimes the question can be asked, these many electrons are there, unpaired electrons are there, what is the magnetic moment? Or what is the hybridization? So those type of questions you can expect. So if that is 4, 4.40, 5, 5.92. Okay, so these are the important part about magnetic moment. So let's move on to CFT. So CFT, what are the questions you can expect is that, how many electrons are there in EG and T2G level? And what is the CFSC value? Those type of questions. So here you can see, there are two types of statement diagram I have written. One is for octahedral. Octahedral, which means the coordination number 6. Then the electrons fill like this. Below I'm having T2G, above I'm having EG. So T2G is dx, xy, yz and zx. EG is dx square minus y square and dz square. Okay, so the same thing applies here as well. Up to D3, no problem. D4, if I'm taking D4, okay, if I'm taking D4, T2G, EG, how many electrons? Either it can be like this or it can be T2G3, EG1. Who decides which is what? So strong field ligand means it get para, weak field ligand means it will continue to occupy the higher level one. Okay, similarly applies for D5, D6, D7. So T2G5, EG0, T2G6, T2G6, EG1. So up to 6 you have to be careful. That is about our CFT. And from the barycenter plus 0.6 del octahedral and plus minus 0.4 del octahedral to T2G2 center point. Center point is called as barycenter. Okay, this is the value formula to find out CFSC value, crystal field stabilization energy. So this is still tetrahedral. If you could see tetrahedral, the T2G and EG, the position is varied. T2 go up, E comes down. Okay, G is not there because tetrahedral is not symmetric. Okay, so just apply to this point. And then the another important formula here you need to know, that is del tetrahedral, which is equal to 4 by 9 of del octahedral. Sometimes they will give you the value and asking for the another one. Okay, so in that case you should be able to do it. Other than this, as I told you, if that is back bonding, stability this increases, and rings are there or chelation is there, will also leads to increase in stability. Okay, so chelation means it's nothing but ethylene diamine, EDTA. So those will have the that will form a ring kind of structure. So that will also increase the stability. Okay, carbonyl compounds will also have a more stability. Other than this, you can go through the uses, biological uses. I'll tell you the biological uses. Hemoglobin, which is in iron, which is in hemoglobin, and magnesium, which is in chloroform. Vitamin B12 is a complex of cobalt metal, and again the magnesium is acting as a catalyst in the photosynthesis. So these are some biologically important points. And other than this, in photographical field, AgBr is used to which will lead to the formation of a complex. Okay, so that's it about the coordination complex chapter. You can score more marks by this. Next we are moving into periodic elements. It is a simple chapter. I'm just giving you the order. Hope this is helpful. If the letter is so small, you can check out our post where I just attached this image also. You can download it and use it. The effective nuclear charge increases if you are moving in the period. Atomic size decreases. And ionization potential, electron affinity, electron negativity, all are in the same category. Okay, so those are increases if you are moving left to right in the period, and decreases in the groups. And the metallic character decreases, oxidation nature increases, reducing nature decreases. You can take a screenshot of it if you want. Here also the whole picture is given over there. And then basic character of oxides decreases and when we are moving left to right. Basic character of hydroxides, hydrides, those are also in decreases. Strength of oxyacids are increases, and it is decreases when we are moving down the group. Stability of nitrates decreases in the period. Melting point of halides decreases in the period. Density will get increased. So the main point you have to remember is atomic or ionic radius, density. These are same category. Ionization enthalpy, electron affinity, electronegativity, effective nuclear charge. These are in the same category. Okay. So metallic character, of course, left side of the periodic table will have high, so that electropositive character will also be high. Okay. So the right side of the periodic table, the non-metal category, that will be low. So that will get decreases. Okay. So that's it about the periodic elements. They won't ask much questions, that will be mingled with the other chapters. So now we are moving on to the group 13 to 18 P block elements. So here I have given the list. You can remember it for the group 13, 14, 15, 16, 17 and 18. So group 13 starts with boron, aluminium, gallium, indium, thallium. And group 14, carbon, silicon, germanium, tin, lead. Group 15, nitrogen, phosphorus, arsenic, antimony, bismuth. Group 16, oxygen, sulfur, selenium, tellurium, polonium. Group 17, which is fluorine, bromine, iodine. And group 18, we all know, helium, neon, argon, krypton, xenon. Okay, these are the mnemonics. You can use it for the quick learning. Why that we need to remember the mnemonics? Because these are following the same pattern throughout the group. Okay. Then electronic configuration, this is a cakewalk to you. I hope you already know about this. Other than this, what kind of questions? What is the syllabus given for your entrance examinations is that the basic properties. Okay, basic chemical and physical properties of P block elements. So first of all, let's talk about group 13. So group 13, boron to indium, the oxidation status, general oxidation state, it can show oxidation state of +3, while thallium can show +1 oxidation state as well, because of inert pair effect. Okay, then the relative stability of M+2, M3+, metal in +1 oxidation state to +3 oxidation state, it goes like this. Barium is least stable, aluminium, gallium, indium and thallium. If I am comparing it with +3 oxidation state, boron, aluminium, gallium, indium and thallium. Okay, so this is the order of stability of the oxidation state. Then moving on to the chemical properties. First, with air, just O2, it is giving oxides, +3 oxidation state oxides. With water, again oxides, along with that hydrogen gas is eliminated. Then with nitrogen, it is giving you Mn, metal with N. So metal can be of anything in the group. Okay, so then with halogens, X2, it is forming Mx3. All the group 13 elements form trihalide except our thallium. Okay, because thallium is more stable in +1 oxidation state, so it will form TlX only. Then with acids, it will form M3+. Metal is forming M3+, along with that hydrogen gas is eliminated. But boron is not affected by the these acids like HCl or H2SO4, while other elements will form the corresponding oxidation state. Then we are moving on to group 14 elements. So group 14 elements, which are carbon family, right? So carbon family, the stability order, which is C4+, which will be higher, then silicon 4+, then germanium, tin, then comes lead. If I'm taking +2 oxidation state, carbon becomes least stable, then silicon, germanium. Why the higher atomic number elements are less stable oxidation state is taking part? Because of inert pair effect. That is an important question you can expect. Here also, this is due to inert pair effect. Inert pair effect is nothing but the s orbital sharing or participation is restricted in those elements. And most importantly, catenation property in this group, carbon is having the catenation property, then leads to our germanium, tin, lead and all, almost not. Silicon is having somewhat a very less catenation property when we are compared to carbon. Okay, and except lead, all other elements in this group show allotrophy. Like carbon is having diamond, fullerene, graphite, right? And properties, chemical properties, with air, it is forming oxides, and the excess of air, it can form dioxide also. The dioxide, if I'm taking CO2, SiO2, germanium O2, tin O2, lead O2, the question can be asked in the way, which of these are acidic in nature? Okay, so these two are acidic. I'm writing this side. So these two are amphoteric and this is basic. Okay, then action of water. So with steam or water is forming SnO2, and action of acids. Acids will not attack the group 14 elements, and action of alkali, that is not also not there. That's it about group 14 elements. I'm just covering the important parts where you can score the marks. Okay, then we are jumping to group 15 elements. So group 15 elements, which are nitrogen, phosphorus, arsenic, antimony, bismuth. Okay, so the question can be asked from the melting and boiling points in case of physical properties. So melting point and boiling point. If I'm taking nitrogen, phosphorus, arsenic, these are having less melting point due to molecular weight, less molecular weight. But antimony, bismuth, these are having less boiling point because of metallic bond. Okay, then talking about the oxidation state of these metals, it can show negative as well as positive oxidation state as we go down the group. The stability of the +3 oxidation state increases along the group, and while that of +5 oxidation state decreases due to, of course, inert pair effect. Okay, so metallic and non-metallic character means down the group metallic character increases. Okay, then we are going to talk about the hydrates. It can form MH3, okay, NH3, PH3, ASH3, like that. Okay, so as we go down the group, the bond angle of these will get decreases. Down the group decreases. What is that? Bond angle. Bond angle like this. Okay, if phosphine is forming the hydrates, then it will look like this. So it will get decreases because of the increase in size and decrease in electronegativity of the atom. Okay, so the hint is that these category NH3, PH3, ASH3, antimony and bismuth. So if in this order, the basic strength, the basicity decreases, thermal stability decreases, and reducing nature also, that is the only case, increases. Okay, then we are moving on to group 16 elements. So group 16 elements where we have oxygen family. So oxygen, sulfur, selenium, tellurium, polonium. So melting and boiling point order, it will follow like O2, S8, SC8, then comes tellurium, then polonium. Okay, so metallic and non-metallic character, the polonium will be more metallic in nature. In this case, the sulfur is more important. Sulfur can form allotropes. It can form rhombic and monoclinic sulfur. Okay, so rhombic sulfur, which is in octahedral shape, that is a pale yellow crystalline solid, and the monoclinic one, text as a again yellow color needle shaped crystals will be formed. Another kind of sulfur is there, very rare, that is an amber brown plastic sulfur. Okay, then we are moving on to group 17 elements where we have halogens. Halogens, which is fluorine, chlorine, bromine, iodine. The physical properties are, except fluorine, all halogens show positive oxidation states as well. Fluorine is most electronegative. So it will follow this order in case of metallic character. Okay, then bond dissociation energy, which is the energy required to break the bond. Chlorine needs more, then comes bromine, then comes fluorine and iodine. Okay, then we are talking about bond length. Fluorine, which will have shorter, stronger bonds it will form due to smaller in size. Then comes other elements. Bond length. Bond strength is just an opposite. Melting and boiling point, again, fluorine is very less. Okay, so this is the order of it. And talking about the chemical properties, all halogens are very, very reactive because that is close to inert gases, which requires only one electron to form a inert gas configuration. So it is very reactive and it is having a reducing property. Okay, so it can reduce itself to, it oxidize itself to reduce others. As they are thermally stable, it's more tendency to release hydrogen easily to show a greater reducing property. And talking about acidic strength of these acids increases down the road. Okay, HI becomes more acidic. So that's it about group 17 elements. Group 18 are inert gases. So inert gases, what I can say about that, they are completely filled. Sometimes xenon can form complexes, form compounds like xenon F2, xenon O, F4, like that. But otherwise, these are completely filled, high in ionization energy. It's almost not able to take the electron out. Okay, so one more thing I want to discuss in P block, that is interhalogen compounds. Interhalogen compounds are nothing but there are few types: AB type, AB2 type, AB3 type, AB5 type, and AB7 type. The only one, this was the question asked, only one type of compound which exhibits AB7 type, that is IF7. Okay, then BF, BR F5, IE F5, so ClF3, all these are made by halogens only, right? Then ICl3, like that. So ClF, so these are the interhalogen compounds. So the oxidation number of central metal atom increases in case of oxyacids. Okay, so that's it about the P block elements. Now we are moving on to D and F block elements. So the general characteristic of transition elements, first we need to know about the electronic configuration, right? So let's talk about the D block elements first. So the electronic configuration is so simple. That fills, one second. So that fills N-1, D 1 to 10, Ns 1 to 2, right? So the transition elements are incompletely filled d orbitals, leading to the unique properties. As we are moving across the period, the atomic and ionic radius decreases due to increase in nuclear charge, and the density and the hardness increases with atomic number due to strong metallic bonding. So remember, these are metallic in nature. Then variable oxidation state, I have just listed the important oxidation states of the elements. So you can just go through it: scandium, titanium, manganese, which is very, very, very important. Okay, so why that is important? Because we are going to see KMnO4 preparation properties, the structures. KMnO4 is a very good oxidation agent because it is in +7 oxidation state. It can reduce itself to its lower oxidation state. Okay, then talking about metallic bonding, transition elements exhibit metallic bonding due to their hexagonal close packed arrangements, body center cubic arrangements. These we saw in solid state as well. These are metallic in nature, and the ionic energies increases because of this atomic number. The 5D elements ionic energies are higher compared to 4D and 3D elements because of its effective nuclear charge and poor shielding effect. This can be asked as a question. Okay, ionic energies. Then we are talking about melting and boiling points. The transition elements will have high melting and boiling points, right? because of strong metallic properties, and melting point initially increases with atomic number, reaches the peak, and then decreases with the atomic number increases. And complex formation, of course, we have seen that in coordination complex as well, because of the availability of the vacant orbital, so that the ligands will come and give the electrons to form the coordinate bond. Magnetic property, which can be found out by mu is equal to n into n plus 2 Bohr magneta, right? The unpaired electrons are n. If that is unpaired electrons, paramagnetic. If that is all are paired, diamagnetic. It can form alloys as well. Then you can see the list of you can take a screenshot of it. The list of basic amphoteric and acidic metal oxides. Okay. Then acidity. As I told, manganese is a very important metal among 3D series. It can exhibit amphoteric, acidic and basic nature as well, depend on their oxidation state. Acidic strength of oxides increases, of transition metal increases with the oxidation number. Most importantly, the questions can be asked from color. In NCERT, you can see a table which mentions the D and F block color, okay, which is super important. The questions can be asked directly from that part. Okay, in JEE Main also they have asked directly those questions. In previous year NEET papers, other entrance examination papers also they have asked a few questions. Okay, so just memorize those colors. I've listed down those things as well. You can check that out. Then why transition elements are forming colors is because of DD transition. Okay, so some elements are not giving colors, like scandium 3+, titanium 4+, zinc 2+ is not giving color. It's because of there is no d orbital electrons to do the 3D transitions. And the observed color, which would be the complementary color of the observed light. Okay, so you know about the color chart, so which is just a complementary color. Then we are going to see about potassium dichromate. The syllabus is that general properties and then potassium dichromate and permanganate. So potassium dichromate, which is having a structure of Cr, 2 Crs, double bond O, one oxygen is used as a bridging, the remaining filled like this. Okay, 2 minus and 2 K plus. So this is a structure of the dichromate. The preparation, as you can see, which can be prepared from ferric chromate with sodium carbonate to give sodium chromate and ferric oxide. That sodium chromate, which is treated with H2SO4 to prepare sodium dichromate. Sodium dichromate treated with HCl to prepare K2Cr2O7. Okay, simple preparation, but 3 steps. The structure I have told you, 2 tetrahedral CrO4 2 minus units are sharing one oxygen atom. The angle, which is 126 degree. Let's talk about physical properties. So the physical property, as you can see, this is orange red crystalline compound. Hope you have saw that in your practicals. They are moderately soluble in cold water, but good solubility is high in hot water. Okay, then chemical properties. Thermal decomposition, K2Cr2O7 is, if I am passing heat, it will form dichromate to chromate and Cr2O3 and O2. Treating with alkali, orange red is converted to yellow due to chromate formation, and this chromate and dichromate is maintaining some kind of equilibrium. Okay, so it is changing according to the pH changes. Then oxidizing power, as I told you, these are powerful oxidizing agents, especially in acidic medium. 1 mole of potassium dichromate in dilute H2SO4 produces 3 mole of oxygen. So that's much powerful this is. And also the main reason is that it is exhibiting plus 6 oxidation state, no? So it can go down also. +2 to +6 chromium can exhibit. Then permanganate. Permanganate +7 oxidation state for manganese it can be prepared from treating K2MnO4 with H2SO4. And the structure of manganate is again tetrahedral O4 minus. Okay, and it is either sp3 or D3s. D3s, I told you in coordination complex, that is tetrahedral. Okay, can be considered as a mixture of sp3 and D3s. The properties of permanganate, which is dark purple crystalline solid, moderately soluble in water, forming a purple solution. It is solubility increases with the increase in temperature as usual. And the 10 mole decomposition, reaction with alkalis, acidic medium, basic medium, this is super important, which will be asked combination with physical chemistry part, redox electrochemistry part, and as well as in mole concept as well. Okay, why that is so important? Because in acidic medium, KMnO4 reacts with sulfuric acid to give MnSO4. So plus 7 oxidation state is converted to plus 2. Okay. In alkaline medium, plus 7 oxidation state is converted to plus 4. Right? So this kind of conversion is super important. The question can be asked from here as well. Okay. So moving on to F block elements. There are two types in F block elements. One is lanthanides and actinides. Right? So lanthanides, starting from lanthanum to lutetium, actinides are actinium to thorium. Right? So these are called inner transition elements because they are having some properties of transition elements as well. So the outer electronic configuration, let's see. So it is entering N-2 F orbital. That's why we are calling that as F block elements. Right? So here you can see the oxidation state and electronic configuration. Lanthanum, cerium, prometheium, neodymium till lutetium. Okay. So the most important part in lanthanides is that lanthanide contraction. So what is that? Is that the decrease in size of the atoms or ions with increase in atomic number. Okay, so that's what the lanthanide contraction is. Why that is happening? It is happening because of the poor shielding effect of F electrons. The questions directly can be asked from this are which of the following statements are wrong, which of the following statements are correct. So those type of theoretical questions you can expect. All inorganic questions will come from NCERT only. So just prepare from NCERT. So the chemical effects because of this lanthanide contraction, the basic strength decreases of oxides and hydroxides from lanthanum to lutetium, and there will be a slight increase in electronegativity and slight increase in electrode potential values of lanthanide series. Physical effects are, as I told you, ionic radius decreases so that the density increases, melting and boiling point increases, and metallic character is also increases. Then actinides. In actinide part also we are going to see the contraction. Let's go step by step. The first one is that oxidation states. It can also exhibit various oxidation states. For example, thorium can show plus 4 so that it can behave like a group 4 elements. Okay, then uranium exhibits oxidation state of plus 6, resembles many properties with the group 6 elements. The plus 3 oxidation state is more stable in F block elements. Color and paramagnetism. Paramagnetism means unpaired electrons, right? So you can expect the number of unpaired electrons questions here as well. Actinides are mostly color. U4, uranium 4 plus is green in color, uranium 3 plus is red in color. The color chart that you can remember. So what is the actinide contraction? Is very similar to lanthanide contraction. It is happening because of poor shielding of 5f electrons. There that was 4f electrons, here that is 5f electrons. Because of that, the size will be decreases, density will be increases, and those stuff. Then we are talking about color. Color is due to FF transition. In D block elements, we saw DD transition. Here we are seeing FF transition. Okay. So F electrons are deeply buried inside the atom. It's not like more exposed like D electrons. It is color is weaker compared to the transition elements, but still they are colored. As you can see, these are colored. These ions are colorless because of completely filled or empty F orbital. Then the differences between lanthanides and actinides, as we discussed, is just a glimpse of it. You can just take a screenshot. Their actinides are more basic, lanthanides are less basic. Lanthanides can form a complexes, actinides have greater tendency to in complex formation when we are compared to lanthanides, and those concepts. Okay, so what are the applications of inner transition or transition elements is that, as I told you, these are colored and which can be used as a very good catalyst. The most important catalyst, that is Wilkinson catalyst, which is rhodium Cl-PPH3 thrice. It is having a square planar structure widely used in hydrogenation of alkenes. Okay, hydrogenation of alkenes. So oxidation states of transition elements. Osmium, which is exhibiting +8 oxidation state. That is the highest oxidation state in the entire periodic table. Then, most importantly, you have to know about the biological role of these transition elements, which is, as I told, iron, which is in hemoglobin, copper, that is in hemocyanin, magnesium, that is in chlorophyll, cobalt, vitamin B12, zinc, that is in carbonic anhydrase. Okay, in case of metallurgical applications, it is used in annealing, tempering, and extraction of silver from coins, ornaments. These elements are used. Okay, and it is used in purification techniques as well. So these are some uses of in transition and inner transition elements. Hope this session is useful. Do practice more and more questions. I am attaching the mock test series as well. You can start writing your test. Thank you.